Compressed air. I don't know a lot about it, but Lonnie Russell does. Fortunately, I'm not the one giving the webinar. Lonnie Russell is. Lonnie used to work in manufacturing, and he has saved a lot of energy in compressed air. And he's going to show you what he did and how he did it. The great news about Lonnie as a presenter is that Lonnie uses a lot of pictures. It's really easy to digest the information he's going to be throwing at you. I hope you like it.
Today we're going to talk about compressed air basics, energy savings opportunities. Mainly we're going to talk about the demand side, but we'll spend a little bit of time on the front end. But why are we even looking at that from an energy savings perspective? Basically, it comes down to motors. 40% of all the electricity produced in the world is consumed by motors, and motors are the real reason that we're looking at compressed air. It all gets back to the motor. So I usually start with this chart because it kind of drives it home. One good thumb rule to remember is that if it's running 24/7, 1 horsepower motor is about $1,000 a year to operate at a typical average 11 cents a kilowatt hour. So that's a good thumb rule to remember. So when you see those air compressors running, they are consuming power and lots of it. Now there's 3 types of air compressors. There's a reciprocating, rotary screw, and centrifugal. Now these are the 3 main types of air compressors. There's still some other like teeth and scroll and some other oddballs out there, but these are the main 3 that you'll run into. Now the reciprocating air compressor, it's also called a piston air compressor, and this is basically just like your internal combustion engine, or you can correlate all these compressor types to a chiller or a refrigeration system too. And just like in a refrigeration system, the piston type is the cheapest, and it's also the least efficient. And it's a positive displacement compressor, and it works, with a piston and a valve, and the crankshaft drives the piston, and the valves bring in the air and get rid of the compressed air or send it out for use. This is the compressor that when you're talking to your mechanic in the shop and all of a sudden something gets really loud and you can't even hear him, this is that compressor. It's very noisy. It's kind of obnoxious, to be honest. It is cheap. It's easy to maintain because it's been around forever and people understand how it works. And it's really good for high pressure, low flow applications, just like a service shop where they're going to air up a tire and then they're not going to do anything. It's got a high outlet temperature. It's hot. A lot of oil gets in the air, so you would never use this for something really a refined type process. And it uses a ton of power. And because the piston action is so rough, it actually causes the air pressure to pulsate and surge. Now, the most common one you'll run into is a rotary screw compressor. And it's also a positive displacement compressor. It uses 2 rotors, as you can see in that picture up here on the left. It uses 2 rotors to squeeze the air and make it and compress it. It can be oil injected or oil free. Oil free is very expensive. It's commonly available 5 to 50 to 500 horsepower. It's pretty much the industry standard. This is the one you run into the most. It's great for higher volumes. It's a lot less noisy than the piston compressor is. It lasts longer if it's taken care of. One thing about this compressor is for the same amount of horsepower, it can be much smaller than a piston compressor and easy to put in. You can just 250 horsepower air compressor, you can use a forklift and set it in place. Whereas with a piston compressor, there's a lot of work has to be done around vibration. This thing is obviously more efficient than a piston compressor. It doesn't add as much heat to the compressed air. You can use just regular old standard rubber isolation mounts to put it in. Now the cons is it's a lot more expensive than a piston compressor. It's more complex, and if you don't run it every once in a while, it can rust. The screws can rust in it. Typically, you'll see this one used in larger industrial applications that have a continuous air demand, like food packaging plants, automated manufacturing systems that use a lot of air pressure. Now the centrifugal compressor is a dynamic compressor. It's not positive displacement. And it depends on the transfer of energy from rotating the impeller at a high speed. Basically, it gets the kinetic energy so high that it runs it into a diffuser. And to simplify it, basically, it transfers the kinetic energy into a higher pressure. This is the highest efficiency that you can get. It's great for higher volumes. It's oil-free by design. The oil does not touch the compressed air. It's lower maintenance, highly reliable. It doesn't have any cylinders. no pistons, no valves. Obviously, the cons are it's very expensive compared to the other two. You need to be careful when you mount it because the high speed can cause vibration, or you need to make sure that you have a good mounting setup for that. And just like a centrifugal chiller, it doesn't like low flow. It can cause surging and all kinds of racket. And it's sensitive to changes in gas composition. It's really used for the biggest of applications. I know sometimes these are also called turbo compressors. And one thing I've seen is you really got to filter the air coming into these. There was one place that was using a turbo blower, and it was a wastewater treatment plant, and they didn't put in their filtration, and every time they'd mow the yard, they'd break this thing. You don't want to be putting particulate into something moving 10,000 RPM. Variable frequency drives. I love these things. I love putting them on motors, but they're a great idea if the load varies. And if it varies 50% or so, it's a great idea to have a VFD compressor, and they are the most efficient compressors you can get, especially a VFD on a centrifugal compressor, because the curve is better. It's a cubic relationship. You'll save, like if you were to reduce it 20%, you reduce the speed of the motor 20%, you're going to actually reduce the power 50%. So if you have a variable load and it's large enough, a centrifugal VFD compressor is the way to go. Now, if the load does not vary, do not buy a VFD compressor. It's a bad idea. You could consume more energy than not having it at all. Actually, if you run a VFD at 100%, it's going to use 3 to 5% more energy than not having it at all. So VFD compressor is great if you have a varying load. And as you can see in the graph here, look at the first one is just a regular old constant speed, probably a positive displacement compressor. Notice that the energy use is way above the actual air demand. It stays fairly consistent. But if you go down to the VFD, it actually follows the demand. So a huge 30% or so savings possible there. Now, when you compress anything, air included, you're going to make a lot of heat. When you throw all those molecules into a smaller space, the kinetic energy goes up and heat will be produced, and lots of it. If you've been in a compressed air room that isn't properly ventilated, you know full well it's very hot in there, and that's why. Now, this heat shouldn't be wasted, though. There's uses for it. And as you can see in this graph, and there's a ton of them out there on the internet, they usually show 90 to 96% of the generated amount of heat is this that can be used. It can be recovered. Well, what would you do if you recovered it? Well, the easiest things are space heating. If it's an air-cooled compressor and you're just running air across it to get all that heat off, why not take that hot air and run it somewhere that you need it? A sock duct, which is a collapsible duct, a cloth duct, they're really cheap and easy. You could just hook one of those to it. I've seen them run through a warehouse that wasn't conditioned at all, but in the winter now, they got the edge taken off of the coldness by running this through there and just taking it off the compressor. You can also use that air to preheat combustion air for a boiler. It's not uncommon to see an air compressor close to a boiler in the same room, in a big mechanical room, or adjacent to it. And that's something I rarely see, but you can use that hot air and preheat the combustion air for the boiler. Now, if the air compressor is water cooled, then you can do the same thing to the feed water of the boiler, or you can use it for domestic heating. And you would do that, if you see on the right there, you would just install a heat exchanger, and you take the waste heat and put it in that domestic heating loop, or you can use it for a process. If you go back a couple slides, you can actually use it for process type stuff too, if you need it for the air dryers or for stuff out in the process heat. Now, this is just an air-cooled compressor, and what I was talking about is you just have this duct here, and you're taking that heat and just blowing it out into the space. It's a freebie. Now, I'm not going to walk through this in detail here, but this calculation shows this is a 100 horsepower compressor, which is very common in factories. And this thing's only running about 50% of the time. And they decided to use the waste heat and heat a space with it. Now, they had natural gas heat before, which is one of the cheapest ways to heat. And basically, this is assuming 0.4 or 40 cents a therm, and actually that's more like $1 now. So this would have saved you about $8,000 a year with natural gas heat. If you had electric heat, it would be especially electric resistance heat, the savings could be 3 times that much. Definitely something worth looking at. Another consideration is the intake air on an air compressor. The cooler it is, the denser the air it is, and the easier it is to compress. So if you can put that air compressor in the shade, that would save money. If you can get it down 20 degrees Fahrenheit, you can lower it by almost 4%. Location obviously is something to think about when you install the air compressor. Like I said, in a shade or a place that would be cooler. If you can put it next to a place that continually exhausts cool air, a hospital would be a perfect case because they often run 100% outside air, and they need to keep it really cold in like the surgery rooms, operating rooms. If you could get close to that, you'd really help the air compressor out. One caution here I'll throw out, I have seen people put air compressors next to the cooling tower because of the evaporative cooling effect, but you have to be careful that you're not getting a higher humidity because that makes the air compressor work harder. It's not real good for it to bring in super high amounts of moisture all the time. Now we're going to get on to where the real money is, the demand side. When you're doing an energy audit, this is where you're going to find a lot of opportunity. Typically, people aren't going to want to rip out their big air compressor and put in another one, but they will listen when it comes down to the lower dollar things that can save them the most money, the most bang for the buck. 65 to 75% of all energy savings opportunities are on the demand side. If you lower your compressed air consumption, you can allow for a smaller air compressor when it's time for a new one, and that could help out on your capital budget as well. So where does our compressed air go in a typical facility? You can see half of it's going where it's supposed to go. Within 5 to 10% is inappropriate uses, and we're going to get into all this in a little bit more detail. Artificial demand's another 10 to 15%, and that's where you run it at 100 to 110 pounds, but you really only need 80. And leaks that can account for 25 to 30%. I hate to say it, maybe more. I used to be a maintenance manager in a few different factories. And, I got to be honest, wasn't a big fan of compressed air. I tried to get rid of it when I could. If I had to use it, I would, but it is not my first choice. And there's a few reasons I'm going to talk about here. One of them is it's expensive. It is the most expensive way to move something, compressed air is. It's very expensive to operate. Repair costs are expensive too. It's inefficient. It takes 4 to 6 times more of it to do the same amount of work that an electric motor can do. Very maintenance intensive. Had nightmares trying to keep compressed air systems running with seals and cylinders and valves, and if the temperature changed a whole lot, the humidity level or the dew point in the compressed air could change. You could get water in the lines, and that causes a whole separate set of issues. I'm thinking like injection molding machines had doors that were operated by compressed air cylinders. And if the temperature changed a whole lot, the door timing would change. It'd have to be adjusted all the time. Just a nightmare for a maintenance department. But a lot of things that have been traditionally used or operated by compressed air, there's more efficient ways to do it now. Let's talk about some of the demand side end uses that you see. The normal appropriate uses, as we talked about, and then air leaks, artificial demand, or inappropriate uses, just kind of summing the pie chart there. Appropriate uses. Where would you use compressed air? Pneumatically actuated equipment, pneumatic hand tools, instrument and control air, and there's still a lot of places where that's always going to be the case. Medical applications and process air. I see a lot in, let's say, an automation for a car factory or a robotics. They would use small amounts of air to blow debris off of the product as they're doing things to it. Really not much of a way around that, but there are more efficient compressed air ways to do it. Process air, a good one there would be like an agitator or an aerator system, such as in a wastewater treatment plant. And we're going to go through some of these solutions for inappropriate uses, like open blowing. You would use a blower for that instead of compressed air. Agitation or sparging, again, you'd use a blower instead of compressed air. Aspirating, a blower. Personal cooling. I see people actually use a 100-pound compressed air line and kind of crack it and let the air blow on them while they're working. We'll talk a little bit about just how expensive that is. It's just crazy how much energy that actually uses. Air-powered diaphragm pumps, and that's commonly called a chugger pump. They have an electric alternative to that now that's also a diaphragm pump. Induced vacuum systems using air, you can just use a vacuum pump instead. Cabinet cooling, you could use a blower or a heat pipe. I have seen a system called the Vortex Cooler that you would hook up to a cabinet with, say, a VFD in it and run 100-pound compressed air to this thing, and it would cool that panel down, but it would use an ungodly amount of energy to do that. And condensate drains, you can go to an airless zero loss drain. So you can see some pictures here of some low pressure blowers, and this is your zero loss condensate drain at the bottom of your, sometimes in the bottom of a large air header, but definitely at the bottom of a air reservoir, you have drains because the moisture will collect there. And they can be manually operated, or they can have an electric one on with a timer. But they have technology now, such as these, that will only let the water out and not the air. Sorry, this picture here is a little fuzzy on the left. Air blow-offs. Now, these are little copper tubes, probably custom made, but you can buy them like that too. And let's take a look at how much money this thing is using. Crazy, huh? It's almost $80,000 to run all this. If you look at the simple payback on replacing that with this low pressure blower is 1.2 years, because the blower uses 4 to 6 times less energy. Look at what an air compressor delivers, about 4 CFM per horsepower, where a blower will deliver, a low pressure blower will deliver 15 to 25 CFM per horsepower. Big difference. This reminds me of when I was a maintenance manager at a big steel mill, the utilities department actually paid the utility bill. So my line, a galvanizing line, did not pay a utility bill. Well, the mechanical engineer was thrilled about that. So this was the world's biggest galvanizing line, had 8,700 feet of product, and every year you'd get problems with June bugs. And the engineer had the big idea of taking a 8-foot pipe and drilling 1/8-inch holes in this pipe and running 100-pound air to this pipe to blow these bugs off the strip before it went through the mill, so you wouldn't compress the buggies into the strip and cause quality issues. He was thrilled to death that he didn't have to pay for that, that he never had to see it. And now that I'm into this side of the business, I realize that that was probably a few $100,000 device that he had running there. Just crazy misapplication. A low pressure blower would have been far better. Regenerative blowers can also reduce the need for compressed air, even more so than a regular low pressure blower can. Now, electric motors use 80% less energy to do the same amount of work as air does. And this is a case of an electric motor versus an air motor. Typically not much of a case to use an air motor anymore. I still see them once in a while, but sometimes they were used because of speed control, but now with VFDs being as good as they are, I don't really know of many applications where an air motor is warranted anymore. Maybe a super wet environment, but even that, they make motors that are pretty tough. And this is just a graph that shows you the difference between using a compressed air motor and an electric motor. Plenty of alternatives to pneumatic hand tools. Electric actuators, they come in all shapes and sizes. They're more repeatable than air cylinders. First cost is a lot higher, but they quickly recoup by the reduced energy cost. And the case in point was when I talked about the injection mold machine that had the curtain that would slide it for personal protection, so you wouldn't get up inside it, so you couldn't stick your hand in there and get it crushed. And it would cycle with the machine. When the machine went in, it would go in. And that was an air-operated cylinder. And as I said, I had big difficulties with that, keeping it where it would time right, because compressed air was unreliable or harder to make reliable. And I replaced that with an electric linear actuator ball screw assembly, and it had encoders inside it and all that. So it was highly repeatable. I mean, yes, it cost more up front, but I never had to touch it again. Once you put it in, it's in there for 30 years. So this is one case where, you know, cylinders, there's a lot of places out there where you'll have air cylinders that can be replaced now with electrical actuators. Let's get to the meat of it with air leaks. You can see, and sorry, this is a little fuzzy here, but you can see the cost of an air leak. A 1/16 of an inch air leak is $1,300 a year. A 1/4 inch is $17,000. This is assuming $10 a kilowatt hour. I know some of you will be very glad to have a 10-cent per kilowatt hour rate. So what can you do about those blow-offs that we talked about earlier? the open tube. And sometimes, people will take the tube and crimp it down, which helps a little, but it's still not the right way to do it. You can replace those with these engineered nozzles, and you can reduce the air use, or you can have savings of 50% or more. Look at how much these handmade blow-offs use. It's just crazy how much they use. Now here's a case right here, well, just a big tube blow-off you'll see, or people mash them. Now I had personal experience where I was a maintenance manager at a CNC manufacturing facility, and we had two 200 horsepower air compressors and a 75 horsepower air compressor, and the 75 failed, and they couldn't get parts for over a month. Now this was a CNC shop, so if any of you are familiar with that, if you drop air compressor much, you can drop tools in the CNC machines. Bad deal. A lot of bad things can happen, scrap and hurt the machines and all that. So, I had to come up with a solution here. One was to bring in a compressor and try to pipe it in, which was a nightmare. So my thinking was we needed to get our air compressor usage down quick. Now I've been looking at this before, but sometimes an emergency presents an opportunity, and we opted to get rid. They had these blow-offs everywhere. The tube blow-offs are everywhere. We replaced them with the engineered nozzles we talked about in the previous slide, and we were able to not use that 75 air compressor. It did not affect the operation at all. So you can see here the difference of a standard air nozzle versus an engineered air nozzle. You replaced all these devices with the engineered nozzles and uses quite a bit less, about, I don't know, 60% less. So one thing you got to ask yourself is why is compressed air needed when the plant is no longer running? I can say I did a industrial audit for Textron, and let me see, it was at the Easy Go scooter plant, and they had a huge compressed air system, and it was running all the time. So I started digging into that, found out it was for a paint booth. So I went to the paint operator and I started digging more and found out that the paint booth that needed compressed air 24/7 had been removed 8 years ago. So they were running 500 horsepower of air compressors on the off shifts for a paint booth that no longer existed. So those are the things you got to dig into. Why do you need compressed air when nothing else is running? Another case here was a bilge pump that would overflow. So they needed the compressed air to operate the compressed air chugger pump to keep the bilge from flooding. Well, replace that with a little 5 horsepower electric chugger pump, and I was able to shut down a 75 horsepower air compressor. Real quick payback on that one. Another one was a CNC machine. The manufacturer in the book, it said that you needed to keep compressed air on the machine for 4 hours after it shut down to keep the encoder from overheating. And I grabbed an infrared gun and I went in there after it shut down, and the encoder was cool within 5 minutes. So sometimes you got to do your own homework. We were able to shut the compressed air down, and they had been operating by this for years. A lot of systems are left on demand, which means they're left on demand just in case you start up, you need them. But if you're on demand, that means you're feeding every leak in the building. So you're better off trying to shut it down and put a programmable isolation valve in, and I'll explain that in a second. But leaving a system on, especially on demand, because some people don't realize that there's always going to be some air leaks. And if you leave it on demand, it's going to run. Regardless of if all your equipment is shut off, it will run. Now, minimize artificial load. We talked a little bit about pressure before. For every 2 psi of increase in the compressor discharge, you're going to increase power 1%. So you need to try to figure out, why was the pressure ever increased in the first place? I love putting in secondary reservoirs at areas, and by that I mean the big tanks. Put them out in the plant close to where the high usage items are. And that'll stabilize air pressure. And that'll keep you from having to crank that air pressure way up. And leak repair, obviously, removing inappropriate loads. Once you repair all your leaks, you may find that you can probably get by with less pressure too. Pressure has a way of creeping up the more leaks there are, because people keep tweaking it up because they can't keep up with the load. I said I was a big fan of the air reservoirs, and you can see in this case, just putting and this is a regular old load unload system, nothing fancy, but putting a receiver on it, look how much it saved per year compared to the others. Just having that receiver on it, that stops it from starting and stopping, starting and stopping. It's a lot easier on the system. Now, it's not uncommon for air leaks to account for 30% or more of the energy cost of a compressed air system. But you need to try to get a culture together that sees that as a problem and takes action when they see it. When you're going after compressed air leaks, it's really important to go after the big audible leaks first. And then you can go after an ultrasound tool to get the smaller leaks. If you don't do that, you can get intimidated by the initial list. Now, when it comes to leaks, I showed you the slide earlier that showed how much the size leak can use per year. Here you can see that even if you can't hear it or feel it, you can be burning $140 a year with a really small leak. If you can feel it but not hear it, it's $700, and if you can feel it and hear it, it's $1120 and up. And this is at 10 cents a kilowatt hour. Now, as I said earlier, ultrasonic is a great tool to find leaks, but do not start with an ultrasonic. You will go out and make a list so long that you won't even want to touch it. They're good for when there's a lot of ambient noise, and they're good for when you've already knocked out the low-hanging fruit, the big stuff, and you want to get to the smaller stuff. Because believe me, there's plenty of smaller stuff out there, but you want to knock out the big stuff first. But this is a very useful tool for finding air leaks. As I said before, running a compressed air system on demand is asking for trouble if everything's shut down, because it's going to feed leaks on demand. So one way that I like to shut down a compressed air system is to just put these programmable valves at the end of the air reservoirs, as you can see in that picture here, and program those valves to turn off. Then the compressor will turn off. It's met. And if it's got a leak from the compressor to that, then you got a bigger issue in piping or something. But if you do that, this does a few things for you. Basically, it allows you to shut down the compressor and not feed leaks, and it keeps this reservoir full of nice compressed air. So when you start up the system the next day or whatever, you're going to have this ready to go, and you're not going to put this huge surge on the air compressor right away. It's a little bit more of a controlled startup to do it like this, but these are not real expensive, and they can save you a ton of money. This would be this was a factory big air reservoir, and this was a valve. I recommended them that they replace it with a programmable valve, as I just spoke about. They had PLCs there too. They could actually control it with that also. Another thumb rule for leaks is typically it's 0.18 kW per CFM. So just a 1 CFM leak equates to 1,577 kilowatt hours of annual consumption. So you can see leaks are a really big deal. You can't get numb to leaks. So one way to help with awareness is back in the 90s, I was big into something called total productive maintenance. I think it's still out there. Basically, it lets the operators get more involved with the maintenance aspect, and they use a tool called single point bulletins. And this is one I put together. I found these leaks all over the plant, and the disturbing thing was there were people standing right next to them working and stuff, and there was no culture at all about air leaks. So you can see in the single point bulletin, I basically say that all these leaks added up would account to about $7,000 a year. And it's totally preventable, and that they need to call maintenance and get this stuff fixed. And that if you hear a hissing sound, it sounds like money, because it is. Now, electric drain valves, sorry about that picture on the left, but you can kind of make it out. They inherently waste compressed air. These are the valves that are on the bottom of air reservoirs, and they operate on a timer. And when they operate, they get the water out of there, but they also remove compressed air with it, which is a bad thing. So they have zero loss electronically operated level sense condensate drains, or oil filled ones too. So you don't lose the compressed air. Now that may not seem like much, but this was at a school I did, and the classes were complaining that once every few days there would be this horribly loud sound right around noon, and then it would go away like 45 minutes later. Come to find out that the maintenance guy would come over here and open that drain valve and leave for lunch and come back. You just saw the numbers on how much money he was costing them. But using one of these automated level controlled condensation valves I just mentioned, drain valves, would eliminate that. And you wouldn't have somebody having to walk around cracking those valves every so often. And this was a factory I looked at, had these two positive displacement pumps, and this was a silicon factory. But the factory was in a building that was originally a different process, and they had a 100 horsepower air compressor, and this was pretty much all this thing was feeding part of the time. So I recommended that they get a smaller air compressor, like a pony compressor, and use it for just this one application. And this was that air compressor. It's 100 horsepower. It unloaded every 36 seconds. It's way too big for what it was being used for. And when you run into buildings that are being used for an application they weren't designed for, this is not an uncommon finding to see something like this. And in the same factory, you see leaks all over the place. It's kind of disheartening to see a hose reel with a big leak, and all they have to do is reach up and shut the valve when they're not using it, at least turn it off. And this is another, what I call an awareness issue around leaks. And just some more air leaks. They're a lot of times they're around filters and oil separators and things like that. Does anyone have any questions? Please fire them in. Okay, I have, what is a typical control parameter for a VFD controlled compressor? Well, typically you would use a VFD on a compressor that has loads that vary probably, I would say 40 to 60%. And you would see, when you're saying control parameter, that would be where you would use it. Where you would control it, it's going to follow the load. So you're not going to tell it what to do. It's going to follow the load and do what it needs to do to maintain pressure at the varying loads. Okay, got another one here. Membrane dryer or refrigerating dryer or other. Now, I'll be the first to admit, not really a dryer expert. Can't help you a whole lot on that one. I don't know what a membrane dryer is. I am familiar with a refrigerated dryer. Refrigerated dryer is the most common that I have seen, but they do have the maintenance associated with them that any refrigeration system has. Sorry, I couldn't help you with that one. Any more questions? I thought I saw one come in, but then it went away.
Yeah, you have one from Anthony Tesk. Wouldn't meters and submeters help find and monitor leaks?
Sure, sure would. You can use flow meters, and especially in a large system, you can use them on the different branches and stuff. And some places go so far as to build individual departments based on those meters. So yeah, you sure could.
And we did get a compliment from someone here, Don. I appreciate it. Lonnie, you do a great job at summarizing all this. And if anybody has questions, Lonnie will send you a detailed explanation. And we could even, go back and forth a little bit more. The email's on the screen. I know we go through a lot of information in these webinars, and I appreciate you guys taking 45 minutes to an hour out of your day. Do a really stellar job, Lonnie, putting it all out there and getting it within the time frame. And I think everybody enjoys that.